Alright, here we are again. Some more physics lectures. This is chapter 7 on quantum mechanics. As noted here, I have made fairly significant changes to the flow of this chapter relative to the text. Basically most of the same stuff, just I felt maybe things could have been ordered a little bit differently, and possibly presented slightly differently. Just the flow is going to be a little bit different than in our actual text. Okay, so we're finally at quantum mechanics, and there's some new ideas here. In a way, we already kind of got into the idea of quantization and some of this weird sort of stuff that happens on very small scales. But there's also new math that comes into quantum mechanics, or at least math that you haven't really seen used in a certain way before. So it's kind of similar to, if you can think back to when you first learned about trigonometry. Trig is almost like a whole different kind of math from all the math that you probably saw before, so it just kind of takes some working with to get used to. The only real way you get used to quantum mechanics is just by doing the math. In that spirit, there is a good amount of math in this chapter, and you'll be seeing a good amount of it in this lecture. We sort of ended the last chapter talking a lot about the hydrogen atom. We eventually got to a model that postulated electrons have this wave-like property, and that led to some very interesting results, be it that the electron orbits around the atom were quantized, and you get these like standing wave results, which could explain the atomic spectra of hydrogen. The usual question that comes after that is, well, it's a wave-like thing, but what is waving, right? And in the last chapter, we just sort of called it matter waves. We'll definitely get more into what it is that's waving in this lecture, but very roughly speaking, what's waving are possibilities. And there's this thing called the wave function, either written as capital psi or lowercase psi, and this is the thing that's waving, and it's not exactly equal to probability, but it is close, and we'll see how it's related to probabilities pretty shortly. Just to note about the notation here, the fonts, the capital psi is usually used when time is included in the wave function, so when it is a time-dependent function. The lowercase psi is usually used when it is independent of time, time-independent function. And it's a little bit screwy. You might see slightly different looking psis here and there, and I don't know what else to do. There are so many different fonts and ways to try to put psi into things, and it's quite annoying because it's really hard to keep it all straight. I tried though. But basically, if it has the top and the bottom and it's symmetric looking, that's the capital psi. If there's no like top or bottom to it, it's kind of tilted to the side, that's our lowercase psi. And psi, of course, being the wave function. Okay, so getting to an understanding of what the wave function is and how it relates to probabilities can be tricky, but there's a pretty nice sort of pathway to that understanding by going back to thinking about electric fields and the intensity of light due to electromagnetic waves and photons. So we've kind of built up some of this understanding already, where now we can kind of use it to maybe transition into thinking about wave-like things more broadly. Okay, jump back to good old double slit experiment, where you're sending in this electromagnetic wave or waves, and those waves pass through these two slits. Light going from each of the slits interferes with the light from the other slits, and eventually all that light lands on a screen and we get this interference pattern. The screen is shown all the way up on the right there, kind of just bright bands, dark bands. Hopefully you're fairly familiar with that now. Also, I threw on here a sort of graph of the intensity of the light on that screen. Right? So peaks up where it's really bright, dips down and goes to nothing where it's dark. There's no light here. And in B, we have a picture of pretty much like what you would see if you did a double slit experiment with some monochromatic light. We have these bands, and just really bright in areas, not bright at all, very dark in other areas, and that's kind of it. As I mentioned though in the last chapter's lectures, you get these interference patterns if you just shine a bunch of light through this double slit apparatus, right? But we understand now that light also has this particle-like quality where it acts like little particles that we call photons. And we're able to control the light or these photons in such a way where if we set up this apparatus, we can be assured that there's only one photon of light moving through the apparatus at a time, and we can just kind of run through this double slit experiment, but basically just shooting one photon through the whole thing at a time. And as I mentioned in the last lecture, if you do that, even though it's still one photon leaving the source, that photon hitting the screen, that's all that happens in one span, and then another photon leaves the source, that photon eventually hits the screen. Right? If you do that, you still eventually build up this interference pattern. So in C, you're actually showing that interference pattern being built up from just essentially no photons laying on the screen to some, to more and more and more and more, and you finally start seeing these bright bands and dark bands. And again, like I mentioned in the last chapter's lectures, you can also do this same kind of experiment with electrons. And you can also do it with neutrons and protons and alpha particles and all kinds of quantum-like objects, very small objects, very low energy objects. Note that I do that little plot on there of the intensity on the screen in all these scenarios, right? When you just shine a bunch of light on there and you get that interference pattern. If you build up the interference pattern by sending one photon at a time, eventually you still get that same interference pattern, right? And that's intensity peaks, drops down, you get this kind of interference pattern, or you get this intensity pattern overall in all these situations. So now if we think back more about how we got to thinking about the intensity of light on these screens in this kind of double slit setup, it had to do with thinking about light as an electromagnetic wave, so that waves from each of the slits had to travel certain distances, and there was a certain amount of wavelengths there. And then a little bit later, when we were talking about diffraction, when we actually calculated the intensity of light on the screen, or the intensity at various positions along the screen, to get also another pattern, diffraction pattern. When we did that, it turned out that we really just had to consider the electric field. And even more than that, it came down to the square of the electric field. That little like graph of the intensity of light on a screen in this double slit setup is proportional to the square of the electric field. Now, if we think about the intensity being built up one photon at a time, right, by these particle-like chunks of light, if you build it up, then the intensity is also proportional to just the number of photons that land at any point on the screen. The reason that this center area is so bright is because more photons have landed there. So intensity is also proportional to the number of photons. Well, then that also means that the number of photons at any point on the screen is proportional to the square of the electric field. So remember, we're talking about this electromagnetic wave. So there's electromagnetic waves that are shining through this apparatus. This is the square of the electric component. Technically, it's the square of the magnitude of the electric field. The probability, then, of landing somewhere on the screen, of a photon landing somewhere on this screen, goes along with the number of photons that actually land there, right? More photons landing there, I mean, there was more likelihood that a photon would land there. So in the end, we could say that these bright fringes are essentially just places where there's the greatest probability that a photon would land on the screen. And in the dark bands, and particularly exactly in the middle, like right where the intensity pattern or where the interference pattern dips down to zero, right, you get these dark bands, and there's zero probability of a photon landing there. So all that together kind of gives us this idea that the square of the magnitude of the electric field is proportional to the probability of photon landing somewhere on that screen. So finally, that gets us to this thing that's waving, the wave function, psi. That is analogous to the electric field. So then in that analogy, the square of the magnitude of the wave function gives us probabilities. A probability may be that we would measure a particle to have a particular range of energy, right, from E to like E plus some delta E. Or maybe a probability you would find a particle in a particular space, say from like X to delta X. So and then here we have some graphs of some possible wave functions. Now, the wave functions themselves are on the left, and then the square of the magnitude of those wave functions then would be on the right. The first one up there, psi 0, it looks like, just sort of this like bump, e to the minus x squared. Psi 1, so this two-sided function, odd-looking function. Psi n, some general psi, not really even or odd, but has these different bumps going on. And if you notice, when you do the square of the magnitude of psi, though, you always end up with positive value. Yeah, so positive, and then this second one, that whole negative side, when you square it, it kind of flips it up onto the positive side. And just to note that the examples of probability you might get from the square of the wave function, I gave examples of energy, position, momentum. Right? Those are very crucial quantities to be sure, but there are countless things that the wave function can include beyond these variables, these quantities. That interpretation then of the square of the wave function as giving us probabilities is what's known as the Born interpretation. Born is somebody's name, one of the physicists in quantum mechanics and the development of quantum mechanics. But more particularly, not just probabilities, the square of the wave function gives a probability density. If you're doing mathematics of probability, it's technically like the probability density function. And being this density, you're usually talking about a range of positions, a range of times, a range of energies, and the probability that a measurement will return something in that range. So in this beginning, or sort of introduction time to quantum mechanics, we're really just thinking about position. We'll think a little bit about the time-dependent wave function, but mostly it's just going to be position, and mostly it's just going to be one-dimension position, namely x. So for most of our purposes, this wave function, when you square it, it's returning a probability density of finding a particle, say, or an object in general, between x and x plus delta x. And since this is a calculus-based course, we generally think about those displacements going to infinitesimal sizes. So instead of x plus delta x, we go to x plus dx, right? Where dx is that infinitesimal change in x. So that if you want the probability of finding a particle, say, between x and x plus delta x, you square the magnitude of the wave function, and then you need to integrate over that range. And so we have this dx in here to integrate over. However, in some cases, the wave function is pretty constant, or it doesn't change very much over like a range that you're interested in. So in that case, you can find the probability just by using the average of the wave function and multiplying by delta x, whatever that actual range of x values is. And again, since we're doing the square of the magnitude of this wave function, we're assuring that our probabilities are going to be positive, which is great, because I'm not sure what a negative probability is, but it's not something that math is going to really like in general. Okay, so square the magnitude of psi, or oftentimes you just say wave function squared, square of the wave function, all different ways to say that you're doing the square of the magnitude of the wave function. So if that gives you probabilities, the next thing we could ask, or the next thing you might ask, is what's the probability of finding a particle anywhere? And we're just talking about one dimension, so x. Anywhere along the x-axis, if you have a particle somewhere there, what's the probability of finding it anywhere along the x-axis? So from minus infinity to plus infinity. From that, we get what's known as the normalization condition. Because if I look along the entire x-axis, there better be 100% probability that I'm going to find the particle somewhere. It's there. If I take the whole line into account, the probability that I find it is 100%, is equal to 1. Mathematically, that means that the probability from minus infinity to plus infinity is now equal to the square of the magnitude of this wave function, and you integrate over all x, that has to be equal to 1. This is our normalization condition. Okay, so that's probably kind of confusing already. It doesn't make much sense. So we're going to try to look at an example having to do with the really simple, or one of the simplest kind of wave functions you could imagine, and see if we can't help make a little more sense of what we're talking about here. So in this example, if you have, say, a ball, and it's contained in a tube. This tube, length L, the ball has got to be somewhere between 0 and L. So the wave function of that ball tells us about the probability of finding that ball somewhere within the tube. The ball is somewhere in there, we can just say it's equally likely that it's anywhere in that tube. That's our assumption, so we can write what a wave function looks like that will give us an equal probability everywhere in the tube. And it's just that. The wave function is just a constant value between 0 and L. Remember, when we square the wave function, we get probabilities. So the fact that the wave function is the same value everywhere is saying that the probability is the same everywhere in this tube. The example says, what is the probability of finding the ball in the left half of the tube at a certain time, time equals 0. And also goes on to point out that the answer should be 50%, because our assumption we're saying is that the ball is equally likely to be anywhere in the tube. So if you ask, how likely is it to be in one half of the tube, it should be 50%. But going through this process and taking this wave function as our sort of assumption, you can see how some of this mathematics of quantum mechanics starts to work out. So we almost have the wave function already. We know it's just a constant value, we just don't know what that value needs to be in order for this to work out the way that we want it to. So we actually know, where we can write down functionally what the wave function is. It's 0 outside of the tube, and we're just going to say c. It's some constant value inside of the tube, between 0 and L. So we can figure out actually what that constant needs to be because we have our normalization condition. We know that 1 should be equal to the probability of asking where is that ball between negative infinity and plus infinity. That's the general sort of condition here in terms of our wave function. This is still the very general normalization condition that we integrate over all of x, we should get 1. Since we know our wave function is 0 outside of the tube and just this constant in the tube, this integral, everything outside of the tube goes to 0, and we know that the wave function is equal to c, some constant value inside the tube, so the square of the magnitude of that goes in for this integral in this region, 0 to L. And since c is a constant, we end up with c squared. Pretty simple integral. C is a constant value, right? So we're just integrating dx from 0 to L. We're just going to get L. But remember, this condition was that that should be 1. We integrated over all of x, we should get 1. So if I then divide by L and square root, let's write that over here. This is telling me that constant value that I didn't really know what it was yet is that. C is the square root of 1 over L, meaning that psi, go all the way back up here, it's not just some unknown constant value anymore. It's 1 over the length of that tube, or the square root of 1 over the length of that tube. Okay, so we constructed the actual wave function, right? We figured out what that constant was. Now we can say, kind of asking this wave function, what's the probability that I'm going to find the ball in one half of the tube? Well, the probability would be from 0, say, to L over 2. Right, we're looking in that space in half of the tube. That's going to look like an integral, 0 to L over 2, and this is the square of the wave function in that region. I'm not going to write the x and t, but they're there. But now we actually know, right, what that form of the wave function is. It's the square root of 1 over L. So this integral looks like, and again, it's a constant, or it's a positive value. This magnitude's not going to do anything to it. And then the square is just going to get rid of the square root. So there you go, that's the integral. This doesn't have any x dependence, so can take it out, and again, we're just ended up with this integral over this region of dx, meaning we're just going to get the size of that region, L over 2. Then the L's cancel out, and look at that, we get 1/2, or 50%, exactly what we expected. So all we did was start out assuming that psi was constant, use the normalization condition, this integral over all of x has to equal 1, or all of whatever the variable is we're talking about, is equal 1, to figure out what that constant had to be. And now that we have it, it gives us exactly what we'd expect. 50% to find it in 1/2 of the tube. Like I said, it's confusing when you first see this stuff. The only way to really get better is to see more of it, to do more of it. So we're going to do some more. Here's part 2 of the ball in a tube example, where instead of assuming that it's equally likely to find the ball anywhere in the tube, we're just going to say, well, what if it's preferentially found in the middle of the tube? There's nothing to say that it should be, but this is just something like, if this were the case, we can construct a wave function that will follow that assumption, and then we can ask for probabilities of finding the ball at certain places in the tube from that wave function. So in this case, the ball is still in a tube, the tube is still length L, but we're going to think of the tube not starting at 0, it's going to start at minus L over 2, which means it ends at L over 2. We can still do this example if it were still at 0 and L, but the book for some reason decided to shift it over. And we should note that the wave function that we're given, it's not normalized yet, we have to do that, but it's only one example of a wave function you could write that has this ball preferentially found in the middle of the tube. You could write all kinds of different functions, or even just draw different functions here that would indicate that the ball is preferentially found in the middle of the tube. Like it could be like a triangle kind of thing. It could just be like this narrow sort of step thing. But in terms of the wave function, it just sort of needs to be the most area should be around the middle to indicate that the probability is highest in the middle. And this is one way to do that. Again, we're only talking about at one time, and we're going to call t equals 0. The wave function we're going to say is some constant a multiplied by cosine of k x. K is the wave number of this cosine function, and the book goes about it a little bit differently of relating k to L, but I think it's not that difficult. Like if you look at this wave, this is half of a wavelength, right? It's half of a cosine function. So half of the wavelength shown here is equal to L, right? The length of that tube minus L over 2 to L over 2, L. So half of this wavelength is equal to L. And just from our basic wave relations, K is related to the wavelength as 2 pi over the wavelength. So you put these together, K here looks like pi over the length of this tube, just from the way we've constructed our wave function. So I know what K is in terms of L, but it's a little simpler to just keep writing K for now, so I'm going to keep writing K while we work out the normalization condition, or what that's going to tell us about the constant A. Remember, if I integrate the magnitude squared of this wave function over all x, I should get 1. That's the normalization condition. So we're only talking about the position. We're only talking about x. So in this case, the wave function is going to be 0 everywhere, but within minus L over 2 to L over 2. So this integral is going to condense down to just that location, otherwise it's just 0. And we're going to end up with just the square of that wave function. So A again is a constant, so I can kind of pull that out. Now to do this cosine integral, it's cosine squared. It's not a very difficult integral, but we're going to see one kind of like this a number of times in this lecture, or in this chapter, so might as well actually show it in a little bit of detail. where we use a trig identity to replace this cosine squared with, leaving off the bounds for now, it looks like 1 plus cosine of twice the argument, so 2kx, all that over 2 dx. So I'm going to bring that factor of 1 over 2 all the way out. We can actually just break this integral now because there's a sum going on here, so write it as two different integrals. Running out of room, dx. So this integral, pretty straightforward, minus L over 2 to L over 2. Again, we're just integrating dx. We're just going to get the length of that region, which is L. It's like a squared over 2. We get L from that first integral. This second integral, well, we'll make a little bit more room here because we actually technically do a u substitution to say u is 2kx, du then would be 2k dx, and so when we do the u substitution, the dx becomes du over 2k, so we get this factor of 2k there. Now we can easily do this integration. The integral of cosine is sine. Sine of u, but we still need to evaluate, and I'm just going to go back to the x variable in order to evaluate that. Because u was 2kx, and now that we're back to our original variable, we're back to our original bounds. And at this point, you can put in those bounds itself if you want to. It turns out that that's going to go to 0. Essentially, it's an odd function being integrated in an even region around the origin, so it goes to 0. So this all ends up being a squared L over 2, but remember, that was equal to 1, right? This is our normalization condition. So if you solve for a, turns out, well, 2 by L and square root. There you go, all that work. A is the square root of 2 over L. So that means our wave function then looks like this. I'm going to get rid of the k as well, just to be very obvious or explicit what's going on here. And this is only in the region from minus L over 2 to L over 2, right? Otherwise it's 0. And then the final thing, we're now asked, what's the probability of finding this ball in the last 1/4 of the tube? So from L over 4 to L over 2, the very last quarter here. That probability is going to look like, well, the probability between L over 4 and L over 2, like integral 4 L over 2. Now, when you square the wave function, that amplitude part gets squared, the cosine gets squared. And again, you see it's a very similar integral that we had before. We go through the same process here. This ends up being 0.091, or about 9%. So there you go, another example of, well, in this case we were given a wave function, or the form of a wave function. We had to normalize it ourselves, but now that we did that, we can then use that wave function to get out probabilities of finding this ball in the tube, even when the ball is preferentially going to be found in the middle of the tube. The wave function was set up so it is that way. When we said, okay, well, what's the probability of finding in the upper quarter of the tube? It should be fairly low because much more likely to find in the middle. And we found it was about 10%. We'll get to more of the mathematics of quantum mechanics soon, but before we do that, we're going to take a little bit of a step back and think about some of the implications or how to understand what it is the mathematics is saying in quantum mechanics. I guess quantum mechanics might be one of the only places where there's still significant disagreement on how to interpret what the mathematics is trying to say or what it's exposing about the world. We're only about 100 years or so out from the advent of quantum mechanics, so maybe it's not all that surprising. But one interpretation is known as the Copenhagen Interpretation. After the Copenhagen Institute, a lot of founders of quantum mechanics were there, born, Bohr, I think some others. Basically, it takes into account this whole probability thing, say that the wave function is something that tells us about the probability of, say, finding a particle in a particular location. However, the result of accepting that is that once you have found, say, an electron to be within this particular region, then the probability will now have changed instantaneously. It's no longer the case that the particle could be in all these different places because it's now here. So if you know that it's in this particular region, the probability that you're going to find it there now, if you were to check again right away, needs to be 100%, right? Because it's right there. You're seeing it, check right again, it's going to be right there. The result of that is that we get this weird thing that's called the collapse of the wave function. So that when you measure the properties of a quantum mechanical object, its wave function can collapse instantaneously. Here we see that sort of picture happening where you got the pre-collapse, we have this wave function or the square, the magnitude of the wave function, and this is kind of standard wave thing moving around, right? Probabilities more or less in different places, but once I measure the position of some particle, say, and I find it to be in this region, the wave function needs to immediately have collapsed and just be a spike right at that region. Whether or not this is something that bothers you or is odd, well, that's kind of up to you. There is something to be said about the fact that it really is saying more about our knowledge of the situation than possibly about some fundamental reality. Then again, what the fundamental reality is gets very confusing. Anyway, I did talk about Heisenberg's uncertainty principle earlier, about knowing position and momentum to a very high degree together is just not possible, or to an extremely high degree, I should say. One outcome of Heisenberg's uncertainty principle is that once you've done this measurement, you collapse this wave function, you have this particle, you say, no, it's right within this tiny little region, that wave function is going to start to spread out again almost instantly. Okay? So even if you measure something, it pretty immediately that wave function starts to spread out, the probability spreads out again. It doesn't just stay like a spike. I guess it's appropriate to note at this point that there are plenty of pieces of technology in our modern world that rely on our understanding of quantum mechanics. So even though it might have some very strange interpretations, the predictions that you get out of quantum mechanics have been put to the test in countless experiments over and over and over again, and those experiments are always verifying the predictions of quantum mechanics. So as whatever weirdness it might seem, it works, and it works very, very well. Almost, maybe we shouldn't have an introduction to quantum mechanics without talking about Schrödinger's cat, because this Copenhagen interpretation could lead you to think some very odd things would happen. So, very briefly, this thought experiment that Schrödinger came up with goes like this. All this stuff is in this enclosed container that you can't see into. You have this radioactive source. You have a Geiger counter which can detect the decay of radioactive material. That Geiger counter is set up to hold a hammer, and if it detects a radioactive decay, it will release that hammer. The hammer then, if it is released, falls onto this vial of noxious poisonous gas that can come out. So if that hammer falls, it breaks the vial. The cat then, in that box, would be killed by the poison, if it was released. It's interesting to note that Schrödinger actually came up with this thought experiment to show how absurd the Copenhagen interpretation is. And one of history's many ironies is that it's still known with his name. But basically, the whole thought experiment hinges on the probabilistic nature of the radioactive source. Radioactive material is such that there's no way to say specifically, to say exactly when a radioactive decay will occur. It's only probabilistic. So you could say after 5 seconds, there's a 80% chance that it will have occurred. But after a million seconds, it's still only like a 99% chance. It's never going to get to that 100% chance. You only get closer and closer and closer. So exactly when that decay occurs, you can't predict. Meaning that you couldn't predict exactly when this counter would detect a decay, when then the hammer would be dropped, then the poison would be released, and then the cat would die. So if you think back to making this measurement of, say, the position of an electron, right? When we did that, the probabilities collapsed. The electron was now right here. The analogy here is that when we go and observe, either the cat has been killed by the poison because radioactive decay happened, or it hadn't, because no radioactive decay has happened yet, so it's still alive. So Schrodinger's thought was that this was just absurd, because you have technically a cat that's in a state that's both dead and alive until you observe it. And just to point out too that the other absurdity going on here that maybe isn't mentioned as much is this implicit assumption that a cat couldn't observe the hammer dropping or the hammer breaking the vial. I'm pretty sure a cat is quite capable of observing something like that. Okay, so back to more of the particulars about wave functions. One thing that happens in quantum mechanics, just to tell you that the number I, being the square root of -1, is just unavoidable in quantum mechanics. It comes up. Whatever you do, you end up with the square root of -1 somewhere. And so it just turns out that wave functions in general can be complex functions, meaning they have real and imaginary components. This whole magnitude square of the magnitude of the wave function then kind of takes on this broader meaning for complex valued functions. When you have a complex function, the magnitude squared of that function now means you multiply that function by its complex conjugate. So down here we show that the square magnitude now means the complex conjugate, that little star or asterisk, is saying this is the complex conjugate of this function. And we're multiplying those two things together. So to actually find the complex conjugate, you might have done this before, but technically you are switching or reversing the sign of the imaginary part of the function or whatever the thing is. In practice, that generally just means flipping the sign of I anywhere in the function, or wherever it appears in the function. And by doing this, if you've ever multiplied something by its complex conjugate, you know that you always get a positive real thing. This assures us that even though we might be dealing with complex functions, we're always going to get real positive probabilities.